Welcome to this lecture series in real analysis. In this lecture, we'll talk about the algebra of Riemann integrability, meaning suppose we are given two Riemann integrable functions, then what can we say about the sum of them or the product of them or some other operation? I mean, there are not many others, but anyway. So let's recall at least two key things from the previous lecture that we will need. So we defined the notion of a Riemann integrable function, which was defined as any bounded function on a closed interval with the property that the upper and the lower integrals coincide. So let me not get into the details of that and recall a key lemma that we proved. So if we have a Riemann integrable function and if we can compose it by a continuous function, then the function that we get out of the composition process, meaning the composite of f with the continuous function, then that function is also Riemann integrable. In particular, every continuous function on a closed interval is Riemann integrable because the identity function is. Alright, and we saw an example of a Riemann integrable function which was highly discontinuous. This was a result of a certain lemma which I don't want to recall. So recall the Thomae's function. We have a function which is defined as which takes 0 on all the irrationals, and if we feed it a rational whose lowest term representation is p by q, where p and q are both non-negative, then we report 1 by q as the answer. So that's the Thomae's function, and we saw that it is also Riemann integrable despite being so horrible, or exotic if you like. Alright, some problems for practice. And I think I've repeated the problem here and the problem there, but doesn't matter. I don't want to erase anything now. All right. So let's see. Suppose we are given two Riemann integrable functions, f and g. Then their sum is Riemann integrable, their product is Riemann integrable, and any scaling of a Riemann integrable function by a real number is also Riemann integrable. So the first one is an exercise. The third one is an exercise. So you can prove it directly or use this to prove that. And let me just say a few words about the second one. Proof of 2. So by 1, we know that this is Riemann integrable. And hence, so is it square because the square function is a continuous function. Composing a Riemann integrable function by a continuous function yields a Riemann integrable function, and therefore this is Riemann integrable. But what is this? This is equal to f squared plus g squared plus 2fg, which gives that the product function, I could have written this directly, the product function is given via this formula. Now this is Riemann integrable. This is also Riemann integrable. Again, the same reasoning. F is Riemann integrable and hence so is the square. This is also Riemann integrable by the same logic. So a Riemann integrable function minus a Riemann integrable function minus a Riemann integrable function is also Riemann integrable. Here we have stated that f plus g is Riemann integrable. You can also, state for yourself that f minus g is also Riemann integrable. Very simple. So this whole thing is Riemann integrable, and we have just divided that thing by 2. So that thing is also Riemann integrable, and that proves that f times g is Riemann integrable. Proving this directly would be a little bit of a pain without using all this machinery, if you will. It would be a little bit painful. You'll be messing around with subdivisions and whatnot. Anyway, so it's a very clean argument. All right. Question arises, can we compose two Riemann integrable functions to obtain a Riemann integrable function? And the answer is no. Unfortunately, I said that Riemann integrability is much more generous than differentiability. It's much easier for a function to be Riemann integrable than to be differentiable. But here this may seem to go opposite to that. If you compose two differentiable functions, you get a differentiable function. In fact, we have a chain rule for that. Here, no. If you compose two Riemann integrable functions, you may not necessarily obtain a Riemann integrable functions, as we are going to show. So how is this justified given what I said? Well, it's because of the generosity of Riemann integrable functions that this is false. There are just too many functions which are Riemann integrable, and therefore you can find two of them to produce a monoid. So what is our counter example? So we have this function f, which takes the value 1 at non-zero inputs and 0 otherwise. So let me just write if x is 0. So f is discontinuous only at one point and hence Riemann integrable. Alright, and what is g? G is Thomae's function. This is the explicit description, but g is Thomae's function, and we know that Thomae's function is Riemann integrable. Okay, great. Now let's see what is f of g. F composed with g. So at an irrational input, we obtain 0 for g. So g of x is 0 for x irrational. And at 0, f takes the value 0. So here we get a 0. And if x is rational, then this outputs a non-zero number. But if you feed a non-zero number to f, you get 1. So here we write a 1. But we know this function is not Riemann integrable. This is not Riemann integrable, as we have already seen many times. So that's it. Composite of two Riemann integrable functions may not be Riemann integrable. And yeah, so with that, I think I want to end this. As usual, like, comment, share, subscribe, and I will see you next time.